In today's video, I'm going to show you how to differentiate piecewise functions. So given f of x equals x squared for x less than or equal to 1, and x for x greater than 1, we're being asked to find its derivative. So just roughly sketching out this graph, we see it's x squared up until that point. Let's say this is 1, and then it's going to be the graph of x after 1. So there are 3 steps we should do. The first step is to check for continuity at the intersection. So super easy to do. That is just f of 1. We just plug in where the graphs intersect. And then that's just 1 squared is 1. And then that's also just 1. So because these are equal, we can say that f is continuous at 1, or at x equals 1. But now we need to see if it is also differentiable at f of 1. So we'll just go f prime of 1 equals. So we'll take the derivative of each. So the derivative of x squared is 2x. And then if we plug in 1 for x, that's just 2. And then if we plug in the derivative of x is just 1. So that's just 1. And we'll see that 2 and 1, they are not equal to each other. So therefore, it is not differentiable at points at x equals 1. So the third and final thing to do is to write our piecewise function in terms of its derivatives. And you'll see why we did the first two in a second. So the derivative of x squared, again, is 2x. But now, because we know that the derivative, or that the function is not differentiable at 1, we'll just say x less than 1. We won't include 1 in the equation. And now this x just becomes 1 for x greater than 1. So we just had to test to see if the derivative existed in the interval. And now that we know it doesn't, this is our final equation. So for our second example, we have a very similar function, but it's slightly different. Again, we have x squared for x less than or equal to 1, and then we actually have 2x minus 1 for x greater than 1. So going through this again, we're going to see if it's continuous at f of 1. So by plugging in f of 1, we can see right away that 1 squared is just 1, and then this is 2 minus 1, which is also 1. Therefore, it's continuous. At least it's continuous at f of 1. And because they're polynomials, the functions themselves are continuous elsewhere. Next, again, we're going to look if they're differentiable at f of 1. So that's 2x, and then that's just 2 times 1, which is 2. And this is going to be 2, the derivative, so this is 2. Therefore, it is differentiable at x equals 1. And then the third step, again, we're going to write this in its general f prime of x form. And so we're going to take the derivatives again, so that is 2x for x less than or equal to 1. So now we get to keep that inequality the exact same. And then this is just going to be 2 for x greater than 1. Now that's our final equation. Now let's do a slightly more difficult example. And so our third example is 3x minus 4 between negative 5 and 0, inclusive of the 0, and then e to the x between 0 and 5, not inclusive of the 0. So again, the first step is to check the continuity at the point of intersection. So right now that's going to be the 0. So from as before, we'll go f of 0 equals, and then we'll plug the 0 in, so this becomes negative 4, and e to the 0 is 1. So these don't equal each other, and therefore it is not continuous. And an interesting property, if it's not continuous, it cannot be differentiable. So not being continuous implies it is also not differentiable, and we don't actually have to perform the second step. It's important to note this is not reversible. So just because it's not differentiable, we saw in previous examples it was continuous. So it's only a one-way relationship. So we can actually skip step 2. I'm just going to say skip. And now for step 3, we just have to take the derivative of f of x, which, just remember, it's taking the derivative of each separately. So this is 3. And then you have to write the bounds. So -5, x less than 0. Again, we remove that equality sign in the inequality. And then the derivative of e to the x is always just e to the x. And then this is just the same as before. And that's our final equation. If you found this video helpful, like, comment, and subscribe.